we can start. Okay, I think we have as of now we have dissertation, not dissertation, we have internships going on, internships, summer internships. Dissertation we have not conducted because we are an online education institution, so we don't have any offline lab. So we are not conducting any offline dissertations. Okay, so I think on to Dr. Bharati.
Yes, sorry. Right. Offline PPT.
Hello. ഇവിടെ വരും ലൈക്ക് അഡ്മിറ്റ് എന്ന് പറഞ്ഞു. ഒരുപാട് ഒരുപാട്
Is my PowerPoint is visible?
Yes, it is visible.
Okay. Good evening, all. So today we are going to learn about the molecular dynamics simulation. So this whole training is divided into two parts. From starting to energy minimization is one part that we are going to learn today, and initially we'll see what are the concepts we are going to learn today. So theory of that part I'm going to explain first, and after that we try to do it in practice. Okay, so and tomorrow from energy minimization to end of the MD run and analysis part is also will be there in tomorrow's session. And after that we can discuss anything. If you have any doubt or any queries, we can discuss.
ഇവിടെ ഈ കുത്ത് കാണുമ്പോൾ അറിയാം. ഉണ്ടോ ഈ ഒരു കുത്തുണ്ടോ?
Yes. I'm going to start with what is molecular dynamics. So what is molecular dynamics? So molecular dynamics is the study of particle or molecule using computational method. So using that we are trying to study the molecules conformation and molecules behavior during the simulation. So there are many properties. It can be analyzed through MD simulation. Thermodynamics properties are there, and molecular conformational part is there, and it is useful in wide range of studies. From we can take fluid for molecular dynamics, and solid particles for molecular dynamics. And, uh, even nanoparticles can be analyzed through molecular dynamics. So it covers uh, more area, and
ലാബില
it is uh, we need a initial structure for molecular dynamics. So coordinates are very important
വോയിസ്
for
ഈസ്
that.
വെരി ലോ.
So it is if you have coordinates of any molecule, it's it's subjected to uh,
രണ്ടാഴ്ച
dynamics.
അയാളങ്ങനെ
So
സംസാരിക്കുന്നത്.
for experiencing dynamics, it needs some
അപ്പോഴേക്കോ ഞാൻ
force,
പറയട്ടെ.
uh, so
ഇരിക്കുന്നോ?
that it will change its conformation,
അതൊക്കെ
and
ഇങ്ങനെയൊക്കെ വരുമ്പോഴേ നമ്മൾ
it
ഇടയ്ക്ക്
goes
ഒരു പറഞ്ഞ്
through
ശരിയാക്കണം.
many changes. So if coordinate is
ഹലോ
changing,
ഡോക്ടർ
yes sir,
ഭാരതി,
yes sir.
someone is saying in the chat box that voice is too low, like that.
Is it okay, sir? Or
Ah,
I need to increase my voice, or
bit more,
it's audio?
bit more,
Okay.
I think. If anything need to be communicated with Dr. Bharati, I think you can switch on your mic and tell everyone, because mic is not banned to anybody. You can switch on your mic and tell, okay? So
Okay.
because he is presenting, he can't shift it to the chat box, that's why. Okay, okay, Dr. Bharati.
Yes, sir. Yeah, yeah. Okay. uh, to coordinator position. So initial coordinate is there, and next uh, next confirmation is there. To change
And
from one
confirm ചെയ്യല്ലേ, റെക്കോർഡിംഗ് ഓണാണ്.
coordinate to another coordinate, it it needs force. So through force, it changes its confirmation. Otherwise, coordinate is there. If you are applying some force on the structure, it changes its coordinates. Okay, so uh, it it goes like this, and
സൗണ്ട് ഭയങ്കര.
means after completing our molecular
എവിടെ
dynamics, or
പോയെന്നോ നോക്കട്ടെ.
once once it ended, uh, we get trajectory of molecular dynamics. So in that trajectory, we have the information of position, that is coordinate, and velocity of changes, and energy of that confirmation, and many parameters are there in the trajectory. It is with respect to the time. So we are executing molecular dynamics for a certain time. So it registers all the information in the early trajectory. So we take final output for analysis. So all these informations are stored in the trajectory. And force field is very important for molecular dynamics simulation. So it is calculating the potential energy of molecule, and it uh, it has many many forces, like it constitutes of bond length, bond angle, uh, torsional angle, electrostatic forces, and water forces. So all these molecular interactions are calculated using the force field. And here in this equation, first term is calculates the bond length related forces, and second term theta minus
ഇങ്ങോട്ട് കൊണ്ടുവന്നടാ.
theta 0 is calculate bond
ഇരിക്കണം.
angle related energies in the molecule, and third term is it
ബാ.
calculates the torsional related energies of the molecule, and after that
ഇവിടെ ഇവിടെ
electrostatic and
എൻ്റെ
van
അടുത്ത്
der
വാ.
Waals energies
കാണാം.
are calculated
നീ വരുന്നോ? കസേര എടുത്തിട്ട്
using
എന്തി
this
മറ്റവളോ?
force field formula. Here
അവിടെ
they
ഇരുന്നോ?
are using
ഉണ്ടായിരുന്നു.
different coefficient for
ഓരോരോ ജോലി തൊഴിൽ
correcting
പഠിക്കുക.
each and every term. So so there are more force field. So each and every software has its own force field, and
കസേര എടുത്തോ.
mixed force fields are there. We may try to use it. Sorry, there is mixed force field, and many force fields are there, and each and everyone has every force field
ഇല്ല
has
ഇല്ല.
its own advantage, and they are
അവരുടെ സ്ക്രീൻ
specially
നമുക്ക് കിട്ടുന്നത്
uh,
നമ്മളോട് വലിയ
designed for particular
ഇതില്ല.
purposes. So targeting particular molecule, they
അവരുടെ സ്ക്രീൻ ഇപ്പോൾ അവർ ഷെയർ ചെയ്തേക്കാം അവിടുന്ന്.
they constituted the force fields, and some
അവരെന്തോ
force fields are
കളിക്കുന്നതെല്ലാം
there
തരും. അതിൻ്റെ കാര്യം എന്താ?
for specifically carbohydrate, and some are there to study the dynamics of liquids. So like that. So based on our interested molecule, there is a particular force field. So we have to use that. If you are using that, uh, the purpose of the dynamics will be very good, and we can complete we can get the information. And next important concept is periodic boundary condition. So periodic boundary condition is defining the whole molecular system. So we cannot do random molecular dynamics. So the whole system has to be within particular boundary. So boundary has to set. So the calculation becomes easy when we are defining the set. Here we are taking one middle box. Okay, so it is in the middle, and it is surrounded by the similar boxes. So the same kind of box is repeated each and every direction of the box, and it is trying to provide the real environment. So we are taking one protein, for example, for the dynamics, and in real proteins are not alone. So in solution, protein more molecules are there in the solution. In the same way, in crystal form, protein is arranged periodically. So in dynamics, we have to have the same condition. For that, the periodic boundary condition tries to uh, repeat the same kind of box in 3 dimension. Here the center box is surrounded with 8 boxes, but in 3 dimension, these there are 26 boxes around the yellow box. So our interest is only one uh, one box. It is protein is protein is in the middle, and it is surrounded with the solvent molecule, and the periodic boundary condition provides the real environment for the box or for the protein. So we simulate only one box, but it considers there are other proteins and other environments around the box. So that is why we are applying the periodic boundary condition. And energy minimization is the next step. Each and every molecule has to minimize before starting the MD simulation. So once the energy is minimum, then only you have to start MD simulation. If you take the random initial structure and straight away you start MD simulation, it it can give artifacts. So for that, so energy minimization is very important, but it is very uh, complicated process. Means it is multi-dimensional. So how many coordinates are there? So 3 times of we have the three three n number of dimensions for calculating the potential of molecule. So it is uh, difficult to calculate, but no, there are many algorithms. They are they calculate the energy uh, using by reducing so many things, and yeah, we have the uh, we have the molecule, and its energy uh, has to be minimized. So there are to to bring the molecule to global energy minimum. It is challenging. So we don't know where what is the energy of our structure. For example, we are taking the protein in this position, and we are trying to calculate the energy of we are trying to bring to minimum energy of the protein, so it may reach here, and we can think that it is its minimum energy. And if you take uh, initial structure at this position and subjecting it to uh, energy minimization, so it may reach this position. Our aim is to uh, bring the molecule into global energy uh, minimum global minimum energy. So for this molecule, it is the global minimum, and further the initial structure has to be here. Okay, then only it will reach this global minimum. So to reach that global minimum, there are many transition state, states of energy. So it reaches here. and we have so many algorithms for energy minimization. There is uh, no particular algorithm for reaching global minimum. So we have to do it in trial and error method. But uh, one particular algorithm will be very good, very good for energy minimum if it reaches if it reaches a minimum quickly, and it must take less memory uh, to do that calculation. Here, I'll share a few two frequently using energy minimization algorithms. One is steep descent uh, method, and second one is conjugate gradient method. So first one is that
Excuse me, Bharati.
yeah,
Hello. Yeah, can you just click on that hide option? Yeah. Okay, fine.
steep descent method is uh, bringing the molecules minimum, uh, bringing the molecules minimum in parallel to the force. So it is going in the direction of force. And here the starting structure is at this position, and force is applied in this direction. So the molecule is moving towards this direction. So after that, the force direction is changed. So the molecule is going towards this direction. Like that, no, it the direction of force changes so many times, and it so the path is also changed here, and it reaches to the minimum uh, in in after many steps. Here the positions gradient and energies gradient is plotted against the function, that is what energy function. And if the starting gradient is here, and its potential is maximum, and as uh, as as the molecule moves, its gradient changes. So its potential is also changing here, and at this position the energy is uh, near to minimum. But in from this position the uh, energy reached minimum, and after reaching the minimum, it again the potential energy is increasing. So it has to stop at this minimum, because no, once it reached its minimum, again the energy will increase. So uh, if the next gradient energy is more, uh, the algorithm will stop at this position, and it will predict this as the minimum energy. So this is how steep descent method works to identify the minimum minimum energy conservation. And, yeah, conjugate gradient method is different, and its direction is conjugated, but the gradient is the gradient change is orthogonal to each and everyone. So first step is here. So next step will be opposite to that, and next step is opposite to that. So
Hello.
it takes orthogonal direction
Hmm?
in each and every
Yes.
change. Uh, Here, it the for
Size.
we have three three variables
Kerala.
in the conjugate gradient formula. So it reaches the minimum energy in three steps. If you have
Bangalore is there.
four, it reaches the minimum energy in four steps. In this case, I think it has five variables, so it reached the minimum energy in five steps.
Okay, okay.
Yes, I think today
Rajasthan, where it
we are
is?
going to learn until energy minimization. So I will stop here. If you have any question
Yes.
related to this, you may ask. After that, no,
Okay.
we can go to practical part of that.
Mm, Maharashtra, where it is located? Okay. So, I'm not interested in these locations. That's so. Bangalore, Bangalore or Kerala, where I don't have any NEET experience. I am working in as a college faculty. I'm working for yes, yes, yes. I recently worked at Chandigarh University, Chandigarh.
Is there any question?
No, I'm presently working nowhere. So I'm seeking job. February, this February. Yes, yes, yes. It's per month 45. PhD. 2016. Okay. Okay. Thank you. Thank you.
Sir, is it okay or okay? If no, there is no question, may start the practical session. Or shall we? No, no, sir, may start the practical session, sir.
Yes, yes, yes. Yes, Dr. Bharati, you can start. It's already recording, so you can start.
Before starting that, I want to say something about GROMACS tool. Yeah. Okay, so GROMACS is free software, and it uh, it can do high-end dynamics using so many advantages in the software. So the software GROMACS, it stands for Groningen Machine for Chemical Simulation. So its short version is GROMACS. This GROMACS project started in the 1991 at the Department of Biophysical Chemistry, University of Groningen in the Netherlands. So they initiated the project in 1991, and it ended there in 2000. So 10 years they maintained this GROMACS software there, and after that, University Uppsala University took care of this project, and they further developed the project, the tool, with many advancements, and till now they are maintaining it, and they are providing this software uh, for academic purpose and all other purposes. And GROMACS tool contains nearly uh, 15 force field. So in that, seven force field are from amber 2, and one force field is from Chong, and Bromo's force field is GROMACS own force field. So they created nearly six force fields with various modifications in that. And OPLS force field is there. So here, hammer force field is specially designed for studying proteins dynamics and nucleic acids dynamics. Or we can analyze protein nucleic acid complexes dynamics using amber force field. And CHOM is especially uh, it is special for protein dynamics, and there are many versions, but only one force field is uh, incorporated in the GROMACS. And all GROMACS force fields are, are good for protein and protein ligand and uh, other other complexes. So uh, it has uh, more applications. Means we can take many kind of molecules for that. And OPLS force field is especially uh, applicable for liquid and organic molecules, and even it is initially designed for studying peptides dynamics. Yes, these things I want to share before that. Yeah, that way I start. Here, initial files for MD simulation are there. I'm going to use that for our analysis. So, first step is preparing protein and converting your protein structure uh, uh, into GROMACS input. That's why this command command is PDP to GMX. So it changes the
Okay, we
PDP
can't see
file format.
any files. We can't see.
Okay, the files are here, sir. Actually,
Okay,
it is
okay.
not. Yeah. And so it takes input file. So I named it protein.pdp, and it gives output as protein 1.pdp. And water, there are many water models for doing molecular dynamics. So it provides the solvent environment in the box. So here I am processing SPC water model, or I am including it in for our dynamics. So last flag, so it will ignore hydrogen in the first step.
Um,
So now,
Hi,
uh,
we are not able to see anything on the presentation. Only the Google Meet is visible.
okay, sorry. So let's share the screen. Previously, I shared different. Yeah. So here the input files are there. So I shared these files with you, and Uh, First command is this. We have to give this command to change the PDB file into GROMACS input. Uh, Whole command is here. It takes this input file and it gives this as output, and uh, I'm giving SPC as a water model for this MD simulation. And yes, if you give enter, it will ask for the force field. We have to select the force field for the MD simulation. Uh, these 15 force fields are here. So this is protein molecule. We have taken protein molecule for MD simulation. So any force field is any for protein processing force field is uh, apt for this, and I'm going to give 14. So GROMACS force field is best in this tool, and the dynamics will be more quick in this tool. So I'm using that. You can choose any force field of
So
your
Bharati,
choice.
one comment is there. Some comments are there in the.
Hello, sir. Uh, this
Yes,
is Manohar. Just have one simple question.
yes.
So you have this number of files that you had sent. We have downloaded it, and now we are using one of the files to simulate it in the GROMACS. I am asking, like, where should those files be? Should they be placed in the same folder in which we have installed GROMACS, or
No, sir. You
how?
can keep the
Uh,
file anywhere in your computer, and you keep all these files in a single folder, and you open terminal from that. Okay, so I did
okay.
that earlier. Okay, I opened my terminal from here. Okay, and it will show where are your files. Okay.
So
Uh,
I am using
yes.
WSL Linux Ubuntu. Is there a way like where I can open this terminal window in the?
Some case, if the OS is having terminal, then simply you can open like this. Otherwise, no. So menu option will be there. From there, you type terminal. So it shows terminal. From here, we have to go to your folder location. Current folder. So it is in the home folder, Bharati, and this is the folder name. So
Okay,
I have to give I have to go to that location by changing directory. cd command
okay, sir.
is useful for that. We will use it
Okay,
for
sir.
to- yes, these things yeah, I think that is starting. These things I didn't have earlier. Okay. After that, no, I process this. I selected.
So Bharati, the sound is too low. Can you just raise
Actually,
it?
I'm using mobile.
Yes, yes, yes.
It's a mobile phone's headphone. That's why
Yes,
the
yes, yes.
sound is low. So sorry, sir. Yeah. Okay, so I selected 14th force field. So after entering that, it calculates each and everything, and it tells the result. Okay, so
Sir, can you show the first command again? Because at that time screen was not visible, so we did not see it.
yes, sir. This is the first command. Okay. Otherwise, tomorrow I will share the commands whatever I am using. So no need to worry about command. Okay. And after processing this structure, it identified these many dihedrals, improper bonds, and these many angles are there. And total mass of the protein is 31 nearly 32 kDa, and the charge of protein is -7. So it creates a topology file after the first step. So it named like this. So topl.top is the topology file created in after processing the first.
Sir, can you post the command in the chat box also, so we can follow it?
Yeah. Yes. It is there. So next task is we have to generate a box around the protein. So uh, I'm taking the previous processed protein PDB structure, and I'm trying to create a triclinic box. Uh, cubic is the box. So the size of the box is here. Okay, so protein molecule is surrounded by cubic box with this dimension. So previously there was no box. Now we have generated the cubic box around the protein.
Hello, Dr. Bharati.
Yes.
Hello. Actually, I'm not getting in. Can you start from the basic steps? So, first of all, I'm not
Excuse me. Yes, sir. Me too. Actually, I couldn't follow you. It's like I thought you'll be giving us opportunity again, or we should follow you now.
Yeah.
Yeah, if you don't mind, can you start from the first step?
Yes,
Means,
that is what I request to.
Okay.
Sir, if possible, can you please go simple and basic because I am a life science graduate. So I'll take a little more time to understand all these stuffs.
Okay. I think
Thank you.
I'm doing this. We did two commands. First, I gave this command. Okay, so this is the starting command for processing the structure.
What is this command for, sir? Can you actually explain in detail, like what this means, what this command is for, what, why I am doing this?
So already I mentioned. Okay, again I will tell you. This command is for changing PDP structure into GROMACS input. GROMACS, so it takes uh, the uh, protein PDP file.
You mean that GROMACS cannot take PDB file, so we are converting it to the file form which GROMACS will take.
Actually,
That is this command for.
GROMACS can process many input files. PDP is one of the format, so we are giving that, and output is also same format. So there is no change in that, but mm, uh, GROMACS tool needs many things. Means topology file is necessary, and in your file,
Sir, what is topology file, sir?
yeah, means PDP. Do you know the what is PDP file or PDP structure?
Yeah, I
It is
think I know
just
it's just a file which can be downloaded from protein database file,
yeah,
which is the structure of a protein, which can be processed easily, like universal file.
yeah, means it contains coordinates of protein molecule. Only the X-ray coordinate means its positions are determined in the PDB file, and nothing else will be there uh, in PDP. In some case, few other information will be there, but GROMACS cannot process only coordinate files. Topology is information about molecules, means each bond angle, diagonal angles, and proper angles. So everything is determined. So you compare this topology file
So
is there.
this topology file will be created by GROMACS later
Yeah, in
after
the
we
first
give
step
this
it is
command.
creating. Okay, so it calculates charge of each and every amino acid. Too. Okay, so they are all uh, they are on the topology file. Okay, so it's a bit complicated and they design like that. Okay, so detail. I think if you are going in detail, we need to.
Sir, this first command will remove water from protein file, and what is this SPC minus IgNH4? This command is for. Is this for minus water to remove water, and what is the next? I want details about this. I am copying and pasting. I want to know why I am doing what this will do to my protein structure.
Okay. Here I am defining that I am going to use the SPC water molecule for the dynamics. Okay, but it won't add water here. So another step is there to add water molecule. So I think third step. In third step, we add water molecule, and here it won't consider hydrogens in the first step. So we are ignoring hydrogen for the process of first step. Okay, I think that
Okay, this water is a PDB, hyphen water or minus water. This is this one.
means each flag has different function. This means it reads this file and it writes this file as the output. And water is just we are giving that we are going to use this water molecule, and we are ignoring hydrogen. So it does this.
Ignoring hydrogen of a water molecule or protein's
Protein, it
hydrogen.
is protein's hydrogen, not water molecule. We are not taking water here.
Okay, okay, sir.
Okay. This is the first command, and second this. Here, edit confirmation is the protein uh, is going to we are editing the protein's shape, or we are defining shape out of shape over the protein. So that is happening in this command. So it takes this uh, protein molecule, and output is this file. So we are creating box. So I named new box for this. Here minus or hyphen C is centering our protein inside the box. Otherwise, it won't center. It randomly